Albert Einstein described himself. In 10 years, Einstein went from high school dropout to formulator of the theory of relativity. How? Why? What can we learn from his career about our most precious resource, the human mind? The secret of Einstein's genius may well lie in his simplicity, his childlike curiosity, his complete concentration, his playful visual imagination, and his openness to the symmetry of nature. But there is something else. The human intellect is a delicate flower, said Albert Einstein. His career reveals how we must nurture the mind to help liberate man from dogma and deception.
Would Albert Einstein plead for a vision that exhibits 1. Childlike curiosity, and 2. Exhibits the symmetry in nature, and 3. Is the culmination of a child's visual thinking, whose audiometric analog is, unequivocally, the prelude to also sprach Zarathustra, and is in fact the uncontestable physical theory of e pluribus unum. Would Albert Einstein express himself with great passion on the question of the making of a motion picture for children worldwide?
I believe that one of the strongest motives that lead men to art and science is flight from everyday life with its painful harshness and wretched dreariness. One who is more finely tempered is driven to escape from personal existence to the world of objective observing and understanding. This motive can be compared with the longing that irresistibly pulls the city dweller away from his noisy, cramped quarters towards the silent, high mountains. Man tries to make for himself, in the fashion that suits him best, a simplified and intelligible picture of the world. He then tries, to some extent, to substitute this cosmos of his for the world of experience, and thus to transcend it. This is what the painter, the poet, the philosopher, and the natural scientist do, each in his own way. Albert Einstein's discoveries in physics ranged from the molecular to the universal. His formative years, the years of his unequaled creativity, were spent here in Switzerland. In his education and his character may be revealed answers to the riddle of all genius. Einstein submitted only 14 lines in response to a biographical request from Susskind. That modest summary conceals one of the greatest adventures in human thought. He was born in Ulm, Germany, on March 14, 1879. Spent his childhood in Ulm and Munich. Went to college in Zurich. After graduation, he became a patent examiner in Bern. Astonished the world with a series of discoveries that transformed physics. Honored by the Sorbonne and by the He returned to his native Germany only to be driven out by the Nazis with other intellectuals like Thomas Mann. He settled in Princeton, New Jersey, and became a life member of the Institute for Advanced Study. His findings in relativity led other scientists to manufacture the first atomic bomb. But Einstein had no part in the making of the bomb and urged nations to renounce it as a weapon of war. Einstein spent his last years at the Institute seeking to develop a unified field theory that would integrate all natural phenomena. He was 76 when he died on April the 18th, 1955. He asked that there be no ceremony, no shrine. Einstein's achievements have been enshrined in memory for time. To trace the nurturing of his genius, one must go back to 1895. In the late summer of that year, a troubled but determined young man of 16 arrived in Zurich. Albert Einstein had fled without a diploma from the rote learning of an authoritarian secondary school in Munich. Einstein came to Zurich to apply. As Einstein explained it,
it followed from the special theory of relativity that mass and energy are but different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is per equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Kocher and Walton in 1932 experimentally.
Einstein's hypotheses were to be confirmed by the unlocking of the atom, the development of nuclear energy, and the making of an atomic bomb. Einstein's energy encompassed even more than the theory of relativity. That privacy was lost irrevocably after the First World War. The name Einstein became a household word, a symbol of man's yearning to salvation through science. His overriding concern was that man learn to control the forces science had unleashed.
To give any estimate of when atomic energy can be applied to constructive purpose is impossible. What now is known is only how to use a fairly large quantity of uranium. The use of quantities sufficiently small to operate, say, in a car or an airplane is as yet impossible. Presumably, all materials which may be used for such purposes will be among the heavier elements of high atomic weight. Those elements are relatively scarce because of their lesser stability. So, though the release of atomic energy can be, and no doubt will be, a great boon to mankind, that may not be for some time.
Despite his renown, the maker science of our century remained simple and unassuming in his person. The secret of Einstein's genius may well lie in his simplicity, his childlike curiosity, his complete concentration, his playful visual imagination, and his openness to the symmetry of nature. But there is something else. The human intellect is a delicate flower, said Albert Einstein. His career reveals how we must nurture the mind to help liberate man from dogma and deception. I am one small piece of nature.
honestly, I don't feel like doing this. This is not something I'm going to enjoy. Why am I doing it? I have 4 kids. They're all grown up. They're brave people. They have made their voices heard. My wife is a brave woman. She is making her voices heard. And I think they're simply waiting for me. Where am I? Why aren't I saying something? So I've decided that I will make a little video and put it on my website. It's a rather popular website. Many, many people see it. And I am going to say something now that may make you uncomfortable. It makes me very, very uncomfortable. But here it is. I'm going to read it. Like most of you, I am worried about the strange and dangerous things that Trump has done since becoming president. Trashing our closest neighbor, Mexico, dictating a very dangerous immigration policy almost designed to recruit more terrorists, bizarre attacks on our press, an obsession with the size of his crowd. And I'm delighted with the protest movements that have sprung up in response. But I have to say I'm also worried that these things are distractions, designed or not, I don't know, which take attention away from something even more sinister. The most dangerous developments to date only made page 5 in today's Chronicle. The purging of Chairman Dunford of the Joint Chiefs of Staff from the National Security Council. His replacement, a man known for his extreme racism and power hunger, Stephen Bannon. The NEC advises the president, in this case a man of great ignorance and very little curiosity, about security matters. Having the ear of Trump, maybe being Trump's brain, Bannon will be the most powerful person on that council. I don't like melodrama, but this is the way the National Socialists began their power grab. National Socialists, I don't think that is something that Bernie Sanders would have approved of. In case you don't know, National Socialists has another name, Nazis. That's the way the Nazis began their power grab immediately after Hitler became Reich Chancellor. Their first action was to purge the security apparatuses of the German states of all Weimar Democrats and replace them with Nazis, Himmler, Göring, and others. Bannon is a man who would have been very comfortable with that crowd. I am worried that the loose cannon acts, Mexico immigration, size of his rally, blah, 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 are distracting us while Bannon slides himself into power. Make no mistake, this is a grab by a clever, devious, and power-hungry man. It is a putsch. This may well be the most important target for our protests. Personally, it scares me more than anything else the Orange Godzilla has done. Please don't ignore it, and please respond with action. Thank you.
It is my great pleasure to welcome you to the second of Lenny Suskind's 3 messenger lectures. Based on the number of people who stepped up to us and introduced themselves to Lenny and tell him how thrilled they are to meet him in person.
Can I ask you to call me by my actual given name, Leonardo?
Leonardo de Susskind. By a gift from Dr. Hiram de Messenger, Dr. Hiram Messenger, a Cornell graduate of 1880 and a longtime teacher of mathematics. The terms of the original gift established, pay attention, a fund to provide a course of lectures on the evolution of civilization for the special purpose of raising the moral standard of our political, business, and social life. At Stanford, including most recently since 2009, the director of the Stanford Institute for Theoretical Physics. He's one of the founders of string theory, actually the one who introduced the notion that particles could be described by excitation states of a relativistic string. Has 4 decades of over 200 cutting-edge research articles, still growing rapidly. His expository gifts have carried over to the popular realm. He's authored a number of popular books on subjects from cosmology to black holes to quantum mechanics. He's been on Nova shows discussing various aspects of physics. On this, I have to move this over. For this poster, I took a screen grab in the upper left from his popular book on black holes and information theory, because he told me at lunch today the audience would be very disappointed not to see at least one picture of an actual black hole at this time. There's also, I think that might be a galaxy. You also requested one of those. And he has a large number of online lectures. This was absolutely extraordinary to me. This is what people know. I searched for Leonard Susskind in Google videos. I don't know if you can see it. This is not a hoax. 281,000 results for videos of Leonardo Susskind. Everything from my friend, Richard Feynman, to my battle with Stephen Hawking. So what I'm going to do now, and it's with great trepidation as to whether or not this is going to work, I'm going to set it up. In honor of this being the second lecture in the 50th anniversary, I'm going to show a 2-minute clip, which you'll see is entirely appropriate, but also great fun, from Feynman's second messenger lecture. I'm going to stop it at one point for an essential observation. Let's see if this works. Genomic screen. These are the identical black holes used by Feynman. Now, when he comes on, he's going to say something about how he had been blinded by the lights in the first lecture, and he's happy to be able to see the audience. But I want it on record that in none of his lectures did he ever complain about the black holes. Will also be an incredibly prescient 50 years earlier second lecture, an introduction to tonight's lecture.
Hi. I can see the audience tonight, so I can see also from the side of it, which last time was a black spot in front of my eyes, that there must be many of you here who are not thoroughly familiar with physics, and also a number that are not too versed in mathematics, and I don't doubt that there are some who know neither physics nor mathematics very well. That puts a considerable challenge on a speaker who is going to speak on the relation of physics and mathematics, a challenge which I, however, will not accept.
And there in the middle of the screen is Lenny. He says no. Let us welcome Lenny Susskind.
All right, I have a couple of things to say before I start. The first thing I want you to know is that I actually did bring a jacket and tie to Ithaca with me. I'm not wearing it, but I did bring it. You know what? I'll prove it next time. I'll prove it next time. Dick was better dressed than I am. The second thing I wanted to talk about was the way I begin lectures. I often write out a couple of paragraphs, and then I actually read them. Sometimes I don't. And somebody asked me, why do you sometimes do this and why do you sometimes not do it? And the answer is it really does depend on what I had to drink before I lecture. Tonight I had a couple of beers, so I have this terrible fear of completely forgetting what I'm supposed to talk about. And so I write a few paragraphs to get me started. So if you don't mind, I will begin by reading my paragraphs. But even before that, I want to second the thing that Dick said. I actually don't know how to aim a lecture like this. I really don't. I have the feeling that, that my problem is similar to our President Obama's. Anything I say will leave almost everybody dissatisfied. But here goes. Quantum mechanics is confusing. I think we will all agree. Oh, actually, I'm not sure. David Merman probably doesn't agree. He understands it better than we do. But apart from David, yes. One of its peculiar features is there are often different descriptions of the same thing that sometimes seem incompatible to our classical minds. A couple of examples that come to mind are the fact that the electromagnetic radiation is sometimes described as waves and sometimes described as particles, but not both at the same time. Another one is that particles have positions, particles have velocities, but not both at the same time. This is confusing. If an electron can have a position and that same electron can have a velocity, how can it not have a position and a velocity? All of this has a name. At least I think it's the right name. It's called complementarity. Now, the reason I'm not sure is I don't think anybody ever had the vaguest idea of what Bohr was talking about when he talked about complementarity, but that's the way I'll use it. To think of a description of this black hole simultaneously from the point of view of Alice and Bob. If you try that, you will run into trouble. One or the other. Either you do or you do not try to find out if Bob was roasted. If you don't try to find out, Bob will fall through with no trouble, but Alice will never know. If Alice does try to find out, she will roast Bob. The evidence is that these two descriptions are not incompatible, but complementary. I will stop at that point, I think. I have lots more, but we're going to stop there. Could I? Okay. You want to go on for another 5 or 10 minutes? We started at 7:30.
Everybody has to vote.
Yeah, okay.
Yes?
This is putting it.
Should he go on or not? Yes.
All right. Okay, we can go on for that one. Oh, okay. That's right.
What about no?
All right. Well, okay, that's very nice. All right. What I promised to talk about in the title of the lecture was the holographic principle. We've not talked about the holographic principle. The holographic principle is another extremely odd, but apparently really, what shall I say, a consequence, a logical consequence of what I've told you. So let me tell you what the holographic principle is. It again has to do with where information is really stored and how much information can be stored, but not for the moment in the vicinity of a black hole, but just in empty space. Let's suppose we have a region of space. There's a region of space. I chose it to be spherical for simplicity. It could be a very big region of space. It doesn't have to be small. It could be big enough to contain galaxies and planets and all that kind of stuff, but of some finite radius sphere. And the question is, what's the maximum amount of entropy that can be in there? The maximum amount of entropy that can be in a region is the maximum amount of information that can be hidden. It's also a measure of how many degrees of freedom it takes to describe that region of space. The maximum entropy of a system is, roughly speaking, how many distinct coordinates does it take to describe that system. All right, so there's our question. What's the maximum entropy can be here? It could be in the form of gas. It could be in the form of Swiss cheese. It could be in the form of people, whatever. How much hidden information can be, or how much information, period, can be inside, or how much entropy can be inside there? All right, so here's the thought experiment we're going to do. First of all, let's suppose that the entropy initially was S in. In stands for initial. The initial entropy is called S in. Now let's imagine that we have a large shell of material. We create a large shell of material out of whatever material we have available, interstellar gas, whatever it happens to be, and we arrange it in a shell, and then we project it inward so that it starts to fall in toward this region. Now let's choose the mass of the shell to be exactly right so that when it's combined with the mass in here, it's exactly enough mass to make a black hole of precisely the same radius. You have to trust me, that's possible. There's no ambiguity about it, and there's no controversy about it. It is possible to create such a shell which is just right to create a black hole of exactly that size. So the shell comes in, crosses the radius r, and leaves a black hole. What's the entropy of that black hole? The entropy of that black hole is the area of the region, just the same formula, times c cubed over h bar g. Most important is that it's the area in Planck units, 4 times that. It's the area in the units of this very, very small Planckian area. What does it say? First of all, the second law of thermodynamics says that the entropy after you do this must be bigger than the entropy before. Entropy increases. Therefore, we learn the following, that the initial entropy must have been less than or equal to, could not have been bigger than the area times this other stuff here. That's a limit. That's a limit on how much entropy could have been in that region of space to begin with. It didn't really depend on whether there was a black hole there or whether there was a shell of matter there. Even if the shell of matter wasn't there, just the fact that we could have created it and sent it in tells us that the entropy in a certain region of space cannot be bigger, can never be bigger than the area of that region in Planck units. That's really interesting because in all other physics, the maximum entropy of a region of space is proportional to the volume. It's also true in most other physics that the number of degrees of freedom that it takes to describe a region of space is proportional to its volume. We have found out by the series of indirect arguments that any region of space can be described by a collection of degrees of freedom which are no more numerous than the area of the region in Planck units. That led to a conjecture. It led to a conjecture that any region of space can be described by some kind of theory describing degrees of freedom on the boundary of the region of space. That is what was called the holographic principle. Holographic because it's like a hologram. That was a conjecture. It was a, you might even call it a speculation, which is worse than a conjecture. But it was in 1994 or so that this conjecture was put forward. Most people at the time thought it was a screwball notion. But it took a couple of years, basically until 1998, until a young Argentinian physicist whose name you should know. I ask people, do you know who Juan Maldacena is? I'm talking about physicists or physics groupies and so forth, and often they don't. Juan Maldacena is perhaps the greatest physicist of his generation. I won't tell you how old he is. He's younger than me, so he's not necessarily greater than me, but but he is certainly the greatest physicist, greatest theoretical physicist of his generation. I'm going to write his name. Maldacena. Mal stands for bad or something, but I don't know what is this? What does bad of, what is Sena? It's Italian, I think. Bad of Sena? Anyway, his first name is Juan. Juan Maldacena produced a perfectly rigorous description of this for a particular kind of space-time called anti-de Sitter space, but that's not what's important. What's important is he dotted the I's, crossed the T's, and found an extremely precise mathematical description of the degrees of freedom on the boundary which would describe a region of space. And indeed, it turned out that there were no more of them than one per Planck area on the region of space. So in some sense, the world is really described by a kind of holographic description on its own surface. Just to make it graphic, everything in this room, there is enough degrees of freedom on the walls of the room to describe everything in the room. It is as if the walls of the room could be thought of as a hologram describing what's happening in the interior. Okay, so we got through the holographic principle. Thank you.
So while you're thinking about questions to ask the lecturer, I have 3 comments. The first is Juan Maldacena will be giving the beta lectures this fall.
I wish I would be here.
We'll see if my...
Yeah. No, I don't think this is going to say anything new. But what I would say is this has implications for cosmology. Remember, in cosmology, I talked last time a little bit about cosmological horizons. Okay? Everybody is falling through somebody's horizon in cosmology, in de Sitter space. Am I talking a language you are familiar with? No. Okay. All right. In cosmology, everybody is falling through somebody else's horizon. And so just the fact that we don't get destroyed every fraction of a second means that horizons are smooth. You know, you're asking a question which I don't know the answer to. How do you make empirical science out of any of these questions? This issue has been around since 1974. It has invaded physics to the point where I would say the majority of papers in theoretical physics, including condensed matter physics these days, is using the mathematics of horizons and so forth. But it really is troubling. All right, let me just put it bluntly. It's very, very troubling that we've entered such a range of parameters that it seems absolutely out of the question to do experiments. Even if I told you that you could do the experiment of jumping in the black hole, I think you would tell me, well, get me the black hole and you try it. But you know, it's a problem. I don't know the answer.
unified field structure of the child's atomistic hierarchy. Millions of people, in particular children, have conceived of the possibility of an atomistic hierarchy, without realizing that deeply within such an assumption on the structure of the universe, there is what the physicists and especially Albert Einstein would call a unified field structure of the pure gravitational continuous type. In 1969-70, an axiomatic treatise entitled On the Structure of the Field 1969-70 was written, which develops the vision of the unified field structure which is manifestly inherent in the child's first architectonic view of an atomistic hierarchy. The vision of the inherent presence of the unifying field structure first appeared to this person on the evening of April 18, 1955, when in third grade, we were taught that all matter is made of atoms. The vision of the pure gravitational unified field structure inherent in the child's atomistic hierarchy is one of extraordinary simplicity which had been overlooked since 1913 and Niels Bohr's solar system model of the atom. It is a highly visual theory that requires only an understanding of 1. The architecture of a child's simple geometric progression, 2. That the universal gravitational field extends in intensity, infinitely far and inversely as the square of the radial distance 1/r2 from the material particle source. Both realizations are possible for most people beginning in childhood. Hence an international film was called for more than 30 years ago. This website documents how the theory was received and censored by the physicists, the academic community, the U.S. press and motion picture industry then in 1970 to 1983 as well as today in 2009-10.
This may well be the most important target for our protests. Personally, it scares me more than anything else the Orange Godzilla has done. Please don't ignore it, and please respond with action. Thank you.